An educative a day keeps unemployment away. Today we're doing interval list intersections. And we have all this body of text, but I think this explains it better, this example. So the intersection of 3, 8 and 5, 6 is 5 and 8 because the intersection of 3, 8, 5, 10 is 5 and 8. And this diagram can help you see it. So we have this list 1, 4, 5, 6, 7, 9. We have this list 3, 5, 6, 7, 8, 9. There's some overlap here between 3 and 4, so we take out 3 and 4. There's also some overlap. Well, 6 and 6 here is actually counted, oddly enough, but it's counted as 6 and 6. Same with 5 and 5. Same with 7 and 7. And then 7 and 9, 8 and 9, we get 8 and 9 because 8 and 9 is inside completely. That's one example. This other example, this second list spans the whole duration of everything here. So we just take from the first list, everything from the first list is the response. I hope that's clear. And we can use this to drive it home, drive the concept of what we're trying to solve home. We have this first list, we have this second list. You see that 1 and 4 are inside 2 and 6. So you get 2 and 4. 2 and 4 is definitely there. 6 and 6. So there needs to be a 6 and 6. There's no 6 and 6 here, so I can assume it's here. So we can walk through the rest and see how it matches. Between 6 and 8 and 7 and 8, you can see that 7 and 8 would fit here, and 15 and 18 in here would fit firmly in here, and the rest don't. There's no intersection for 10 and 13 and 20 and 24. And you leave the explanation. 1 and 29, wow, that's very long. Everything here fits in, so pretty much I can just return the second list. This is weird. Shouldn't end in 29. Should end in 20. That's 20, not 29. It's a close one. Okay, that's it. Then they want us to figure it out. I'm gonna just ask for the solution because then you can look through it, compare the start and end times, move forward. You can pause and view this, what this says. I'm not gonna spend too much time on it. The diagram explains the optimized solution to the problem. We need to have a start and end variable that we're going to use to populate a list, a resultant array, that is the array we're going to return, called intersections, and it lists what you do. So move array by array. The first element that occurs later, because 2 is after 1 here, we store start as 2, and because end is the same, we store end as 4, and then we add that to the resultant array. This is the array we're going to return. These are our input arrays. This is the array we're going to return, and we do the same thing next time. Start are the same, so start is 5, and this ends first, so it's 6, and so we add 5, 6 to the resultant array, and we keep moving. In the event where sometimes we move, I think sometimes we move, and the code will probably show it. Sometimes we move and we don't have this happy path where they have the same start and end times. So I'm sure we'll see an example of that in the code solution. But the same thing, you do the same thing there and you wind up with this and you're done. All right, next we're gonna look at the code. I must set it up real quick. All right, this is the completed solution, TypeScriptified, completed TypeScriptified solution. And we have 2 arguments, interval list A and B, and we're going to return this variable, intersections, right here. Let's step through the code. I'm going to zoom in a bit more so you can see it on the phone, and we get to it. It's an interesting first case. So we're evaluating these two arrays to see their intersection. They're the same, so we expect this to just populate with that, with 1, 2. We're looping through, using I to loop through the index variable I to loop through the first argument, and J to loop through the second one in tandem. All right, let's step through it. We're going to update start. It's going to give us 1, really, because maximum between this expression here. It's just going to give us 1. Now we can watch it before it even executes, because we have like watch variables here. Running out of room, but it's going to give us 1. I don't need to see. Oof. Control Z, can I Control Z that? No, I cannot. Okay. I want to get rid of this. We don't need to know where I and J are exactly. What we do need is to keep track of start and end before we even get there, so we can say with confidence what's going to happen. Okay. Yeah, let's keep going. So start is going to be 1, end is going to be 1 for sure. Start less than or equal to if they're the same. So this is the guard that helps in cases where there is no intersection, is that we push it here in the event that the start is less than the end. I'd like to see an example where that's not the case. Yeah, and then if this is less than this, oh, so whichever interval ends earlier, right? Whichever value ends earlier has a earlier end value. Increase its cursor, because I and J are just cursors looping through our input arrays. So in this case, this is false, so J is going to move forward, right? And then J is now 1, and we've already moved through. Whenever we move through any one of the input lists, we're done. And since J is going to be 1, and the length here is 1, this is going to break out and we're done. Return the intersection. That's it. That's all. So if I just keep playing this, it's going to tell me the intersection or blah, 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 blah. That's not very accurate, but I think you can follow along regardless. What I want to do now is I want to watch something like this. So I know the thing I deleted. That's how to like see an array in a string format. So this is our array A, this is our array B. This one is more interesting, and this, but before I come back to the solution, I'm going to break pattern a bit. Step through the time complexity n and m, which is a linear time, really. They are the number of meetings in A, O of big O of n and m in A and B respectively, and the space complexity is 1 because we're not, because of this reason, fixed amount of memory is consumed by few temporary variables for computation, right? Let's look to this example. So start is gonna be 2 because it's evaluating these two. This comes after, right, after 1. So 2 is gonna be the start, 4 is gonna be the end. Start is less than the end, so add it. I want to see a case where the start is not less than the end. All right, this second example is a case where this branch doesn't execute, and it happens somewhere around here. The cursor somewhere around here. So we're going to step through for the first pass, start and end is 2 and 4. 2 is before 4, so we add it to our output list because that means there's an overlap, an intersection. Next, because 4 is not less than 4, we're going to increment the cursor j, not I. And that's arbitrary. We could have done it either way. Okay. So now the new start is going to be 5 and end is going to be 4. Because j is now here, whereas the smallest, interesting. We're still evaluating 4 here because I is still here, right? Whereas j is here. It's on the second list, but I is still on the first. The first list. So it's not gonna add anything to our return, what we're returning. Instead, it's gonna make it so they are evaluating apples to apples, like these two over here. So now they're evaluating the same thing. Start is going to be 5, and it's going to be 6. So that's an intersection because 5 and 6 fit snugly in here. And now because 6 ends before 7, we're going to increment I. So I will now be looking at this, and comparing it to this one. Exactly. I is looking at 9. That's why 9 is here. And it's comparing it to this. That's why 7 is here. 7 is less than 15, but 9 is greater than 5. And it's another case where this branch is not going to trigger. And because 15 is not smaller than 7, because 15 is not smaller than 7, we're going to move j, the cursor, to look at this so that they can look at each other. So j goes up. Nice. It does make sense. All right, and that's it. We can look at more examples, but this looks like it checks out. So thank you for watching. See you tomorrow.